The first time we actually start to quantify acid base is actually use the litmus paper. I guess everybody have done this in your Gen Chem experiment. So the really important thing is actually starting from here. After we start to define this value pH, okay, we have a very quantitative way to know the solution is actually more acid or more basic. That's the quantitative definition of pH. So you measure the concentration of H+, which is actually proton, not hydrogen, proton, H+, inside your solution. Once you quantify its concentration, you take the negative log of that quantity, and the value you get will be the pH. That means actually in your water is going to dissociate into H+ and OH-. Let me write it out. H2O liquid, it can undergo the H+ and the OH-. This process will happen inside your water. But you only have a very small portion of that happen because we know the pH of your water is 7, right? That means the proton concentration inside your water solution is 10 to the -7 m. You know the proton concentration inside water is actually extremely low. Why is this? Actually inside your water solution, majority of the water existing as H2O molecule is neutral. And only very small portion of the water will become H+ and the OH-, right? And the H+ concentration and the OH- concentration is equal to 10 to the -7. The dominant species is actually your water molecule, H2O. But you also have some little amount of H+ and the OH-. It is those H+ contribute to your pH, not your water, okay? It's the H+ contribute to your pH. This is actually a very important concept that you should know. So with that concept in mind, you should know that the pH is defined as this. And then if you have acid, that means the pH is smaller than 7. If it's actually larger than 7, it is basic. So if pH equals to 7, we call you have a neutral solution. And then if you have acidic solution, that means you have more protons than the hydroxyl anion. If you have a base, that means you have higher concentration of OH-. So this acid-base concept become very systematic introduced by the two scientists. Of course, Arrhenius is actually the one that defined the acid base the first. He defined the acid as a species that can generate excess H+. We call it species as acid. And then if the things, once you throw into water, it produces excess OH-, then it defines that species as a base. For example, if you throw in your HCl into water to form the HCl aqueous solution, HCl is going to produce H+ and Cl-, right? Since you throw in HCl, you actually produce more H+ inside your water. Then we call the HCl as an acid. If you throw in your sodium hydroxide into water, that is going to produce more OH- inside your water solution. Therefore, based on Arrhenius' definition, sodium hydroxide, it is a base. But very soon, scientists found there's actually a limitation. Because this actually limits, you can only define the pH inside your water solution. But when we do the organic experiment, okay, you realize most of the experiment you did is not actually in aqueous solution, right? It's always in the organic solvent. Okay, so we need to have a better definition for the acid base. That's why we have this Bronsted-Lowry theory. Okay, so what it says, instead of using the H plus and OH minus, we just use H plus as my acid definition. Okay, so he defined the acid as a proton donor. That means it's going to give out a proton to some other partners. We then call it that species as a acid. In contrast, for the base will be the proton receiver or the proton acceptor. Okay, so the guy who actually accepts the proton will be defined as base. For example, if you have an HCl plus H2O, and then you produce H3O plus and the Cl minus. In this case, you can see your HCl become Cl minus. It means it gives out the protons. So this is actually a proton donor. Therefore, we say HCl is actually an acid. On the other hand, if you look at this water, water goes from H2O to H3O plus. It actually receives the proton. Therefore, the water will be the base here. Okay, so when I write these equations, okay, those equations on the reactant side, you already have the acid and base. Another example is here. If you look at this equation, you will realize your NH3 become NH4 plus. You actually receive one proton. Therefore, this will be defined as a base. But for your H2S, it becomes SH minus. Guy is actually losing a proton, right? So this is actually a proton donor. Therefore, the H2S is an acid. It is very important that if I give you equations, you actually compare your reactant product and define the acid and base inside your equation. Okay, this is actually one of the first things that you need to learn for this chapter. This table actually summarizes all the things we say, where we say in the Arrhenius acid-base theory, the way you define acid-base is really depending on what species you generate, right? If you generate H plus, you are actually acid. If you generate OH minus, you are base. And then all these things is very useful if you have aqueous solution. However, to make these things more general, later on, Stellori actually provide another theory. It defines the species that provide H plus as an acid, the species that accept H plus as a base. This is actually the concept that we're going to use a lot in this chapter. We're going to expand this concept a little bit more so we can actually bring up the concept of conjugate acid and base.